So, we will continue our class on atomic and molecular physics. So, in first class we have seen the Dalton's hypothesis, which basically first tell about the atomic nature of the matter in 1808. And in 1808, this Gay-Lussac discovered that two gases combine to form a third one. The volume are in the ratio of simple integer. So, basically in case of Dalton's hypothesis, the chemical combination that was tell in terms of the basically in terms of number, okay, or atomic weight. So, that gives the sense of that combination in number, and that also possible in terms of volume. So, that is the Gay-Lussac discovered. So, then in 1811 Avogadro hypothesis, this you know this Avogadro number. So, that is Avogadro hypothesis. What is that? The equal volumes of different gases contain equal number of atoms or molecules, right. So, and from this hypothesis Avogadro first time clearly mentioned or clearly distinguished between atoms and molecules. So, atoms basically he described as a discrete particles of an element or an substance, and molecules basically the discrete particles composed of two or more atoms bound together. Okay. So, he is the first to make clear distinction between the atoms and molecules. Okay. So, in 1865 J.L. Lord Smith made first estimation of the number of atoms or molecules in 1 gram mole of gas. Okay. And he estimated and he found this number which was not very accurate, because he was taken data from the he used this kinetic theory, and then in 1907 J. Perrin considered the Brownian motion, suspended particle in a liquid, Brownian motion, okay, suspension of particle, motion of particle suspend in liquid or in a medium, and deduce the number of molecules or atoms per mole, and he reported the value of Avogadro, which is called now Avogadro number, that is close to the modern value of Avogadro number. So, that is the modern value of Avogadro number is basically 6.022, or sometimes people tell 023 into 10 to the power 23 atoms or molecules per mole. So, with time it is clear about the nature of matter, atomic nature of the matter. So, matter is made of atom, and atom is taken as a spherical ball kind of things. Okay. They are not breakable. Okay. They are in motion. So, that is the origin of temperature, pressure, viscosity, thermal conduction, etc. Okay. And one gram mole of any substance, it contains Avogadro number of atoms or molecules. So, that is also a nice development. So, that was the sequence of understanding about the atomic nature of matters. So, now I think now next question is the constituents of an atom. As I shown earlier, that constituents of an atom, basically we know now that electron, proton and neutron. So, how it was discovered. So, if we want to know that one, so this first Faraday's laws of electrolytes. So, that is the first law which tells about the existence of electricity or charge. So, that time it was not called charge, it was called electricity. So, Faraday's law of electrolysis. So, that is basically, if you take a container, and in container you take the solution of some substance. Okay. So, that is basically called electrolyte. Okay, that is the solution of a substance. Now, if you put two electrode, okay. Now, this electrode, say this is the negative electrode, this is the positive electrode, this voltage is applied between these two electrodes and current is, so current will flow through this electrolyte, and it is found that if electricity, that time it was called electricity is passed through this electrolyte, then the mass of the substance is liberated on the electrode, means mass of that substance is deposited on the electrode. So, the mass of that substance deposited on the electrode, if it is m, this mass, it is the m. So, that is proportional to the electricity Q, So, if current passes, basically if electricity passes for a certain time t, so that means this, if current passes through this electrolyte for a time t, so this mass deposited on the electrode, so that is basically proportional to the electricity, proportional to the current, and proportional to the time. So, that is basically the charge. Okay. So, mass deposited on the electrode, that is proportional to the charge. If we if charge flows more and more, so mass deposited on the electrode will be higher and higher. And for a particular, for a given substance, that first one was for a given substance basically, and second one is so this for a given substance, okay, and for a given electricity, for a given Q electricity, that means if same amount of charge or electricity passes through the electrolytes. Okay. So, this mass for different substance, this mass is proportional to the equivalent weight of the substance. Okay. Equivalent weight of the substance. What is equivalent weight? So, that is basically the atomic weight divided by the valency, atomic weight divided by valency. So, for monovalent, valency is 1. So, this equivalent weight is basically equal to the atomic weight. Okay. So, this m is proportional to the equivalent weight, say mu by nu. So, mu is atomic weight or molecular weight, and nu is the valency. So, basically it's for a if substance is constant for a particular substance, m is proportional to q, and now for a given q, for a particular amount of charge or electricity, that means for different substance, this mass is proportional to the equivalent weight. So, that is atomic mass by valency. So, in general then we can write m is proportional to q mu by nu. So, it is now this is general, it is not for a particular substance, it is not for a particular charge, it is general. Okay. So, now this proportionality constant m equal to its constant mu by mu. Okay. So, mass deposited on the electrode or mass liberated during the electrolysis. So, that depends on the atomic weight, valency, and amount of charge passes through the electrolysis. So, from here, so that's the basically Faraday's laws of electrolysis, and from here if you take monovalent substance nu equal to 1, then you can write m equal to q by f, and if so, So, if you consider that for monovalent the amount of substance deposited on the electrode. So, if it is m equal to mu, if it is equal to the atomic weight, so then you can write that Q equal to F. Okay. So, F is nothing but the charge, right, or electricity. So, F is called Faraday constant, F is called Faraday constant. F is called Faraday constant, okay, and its value. So, it's basically amount of charge or electricity which passes through the electrolyte for monovalent substance, then the mass deposited on the electrode, that is basically its mass is basically 1 atomic weight or atomic weight. Okay. So, it is the 1 gram mole mass of 1 gram mole. So, for any monovalent substance, solution or electrolytes taken of that substance, so F amount of charge or electricity passing through this electrolyte always gives for 1 gram mole amount of metal deposited on the electrolyte. Okay. Now, if nu equal to 2, then you can see if nu equal to 2, not 1, then mu equal to m, in that case Q will be equal to F into. So, in that case, if nu is not equal to 1, okay, then your Q will be equal to nu into F, okay, nu into F. So, as I told, this F is Faraday constant, this has constant value. See, its value is basically 1, its value is what is this value? I think I have no, I have not written. So, here I have value 964853, 964853 coulomb per mole, okay, coulomb per mole, and this is called basically this Faraday constant, this the in terms of coulomb. So, this equal to, we tell this 1 Faraday, also we call. So, if you pass 1 Faraday charge or electricity through the electrolyte, okay, so you will get 1 gram mole mass deposited on the electrode. Okay. So, if valency is higher, if say 2, then you need 2F amount of electricity charge to release to get deposited on the electrode of 1 gram mole substance. Okay. So, from here basically some hints we get about the existence of elementary unit of electricity. So, this in electrolysis, so some charge are flowing, okay, electricity passing through it. So, that how it is happening. So, it is the, so these atoms have some charge or electricity attached with the atom, charge atom, and motion of the charge atom, it is motion of the charge atom towards the electrode, and after reaching to the electrode, so this mass of that atom is liberated or deposited on the electrode. So, this kind of implication one can get from this Faraday's laws of electrolysis. So, next in 1874, G.J. Stoney proposed that there is a natural unit of electricity, and this unit should be taken to be the quantity of electricity which must pass through an electrolyte solution in order to liberate one atom, not atomic weight, one atom of a monovalent substance. Okay. So, what is telling, there must be some natural unit of electricity, some smallest value of electricity, and if you pass this unit, this amount of charge, this unit amount of charge through the electrolyte, then the one atom should deposit on the, will deposit on the electrolyte, or will liberate one atom of a monovalent substance. Okay. So, here basically one charge attached with one atom. So, this kind of proposal made by the Stoney, and later on, if so, according to Stoney, if so, then 1 gram of substance, it contains Avogadro number of how many atoms? The Avogadro number of atoms, and if each atom is having, a unit, smallest unit of charge, right, smallest unit of charge. Okay. So, any number of atoms, which is deposited on the electrode, if you pass current or electricity of 1 Faraday, okay, F amount. So, this n number of atoms, each atom contains a unit of charge, smallest unit of charge, and so then this for 1 gram mole, so total charge will be this, and that should be equal to the 1 Faraday, because if you, that already is known from Faraday's law of electrolysis. So, that if you pass 1 Faraday electricity through the electrolyte, then 1 gram mole for monovalent, 1 gram mole of mass will deposited on the electrode, and 1 gram mole of substance, it contains Avogadro number of atoms. Okay. So, from here from here one can estimate this, that unit, natural unit of electricity, that is E equal to F by Na. Okay. So, that time it was estimated, and the value was calculated, that is around 10 to the power 20 coulomb, 10 to the power 20 coulomb. So, that it was not so accurate because of the Na value, Avogadro number value. During that time, there is Avogadro number value, whatever available from kinetic theory, that was not accurate value. So, that is why that error was there inside, but in principle it was calculated the unit, natural unit of charge, the smallest unit of charge, that is E. And I think this name of this electricity, it was that time it was called that this amount of charge, that is called electron. The name was given electron. First time that word was used to express about the amount of charge. It was, name was electron. Later on, actually it was changed. Actually, we later on this name of that smallest unit of charge, that was given electron. Okay, not amount of charge, but that time that electron was used to express the amount of charge. So, then in 1880, Helmholtz pointed out that it is apparently impossible to obtain electricity in smaller amounts than E. Okay. So, means that is the smallest unit of charge. We cannot get smaller value than this. So, that was the prediction or hypothesis or assumption. Okay. So, but in 1987, J. Thomson made first direct measurement of this smallest possible charge, but that was not very accurate, and basically it's from J. Thomson's experiment we get the specific charge, that is the charge E by m, that E by m, okay, E by m, and but in 1909 R. M. Millikan made the first accurate measurement of E in his famous experiment, you know, that oil drop experiment. In that experiment he directly measured the value of E, value of the smallest amount of charge. So, that value was received at 1.6 into 10 to the power minus 19 coulomb, Okay. So far whatever I have discussed, that this one constituent of atom is the electron, and what is the amount of that what is the smallest unit of this charge of this electricity that contain that electron. Okay. So, that was experimentally measured by J. Thomson and Millikan. So, next we will see about how this Thomson measured the specific charge in his experiment. So, so for this basically, so we have two tasks now. We have two tasks now, basically this J. Thomson experiment, okay, which measured the E by m specific charge, and then Millikan's Waldorf experiment. So, it gives the measurement of E. Okay. So, I would like to discuss about the experiment. So, it is a very interesting, and during that time that experiment was done. So, for Thomson's experiment, this discharge tube was used. What was that? The discharge tube is a closure, nearly glass tube people taken, and one electrode here, another electrode is here. Okay. So, positive charge was highly, very high voltage was applied. Okay. Very high voltage was applied between these two electrodes. So, this is basically called cathode, and this is called anode. Okay. Now, if pressure of this tube is decreased, means if it is evacuated, means pumping, there should be pumping arrangement, pump is attached with this tube and pump out the gas from the inside, and we use gas inside of this, first evacuate and then we also control the gas. So, you can take any gas, okay, hydrogen gas or other gas, argon, other gas. Okay. So, inside gas is in a very low pressure. So, it is a low pressure is maintained. Now, if you apply very high voltage between these two, cathode and anode, then it is found that if it is take hole is there, if hole is there here, so it is found that there is a ray passing through it and hit on this edge, and sometimes if you use fluorescent material coat on this edge, or you can tell that if you put a screen here, so you will see that some rays is passing through this anode. So, these rays is basically called the cathode rays. This rays is called basically cathode rays. So, that was German physicist basically Goldstein. He discovered that cathode ray. Okay. And so, this cathode ray was used for Thomson experiment using the discharge tube. Okay. Now, in cathode ray, and it was known, and I think Goldstein discovered this cathode ray, I think it is around 1870 or 80, that I think around 80, yeah, exactly I didn't remember, but anyway. And after that there are some study on this about the nature of this ray, and for that earlier study it was clear that this cathode ray is basically the is the ray of the negative charge, ray of the negative charge, ray of the negative charge. Cathode ray is basically ray of negative charge, okay, negative charge, and yeah, and also it was known that this ray is independent of the material of the electrode, means cathode and anode, as well as it is independent of the nature of the gas used in the tube. Okay. So, this was known from earlier study. So, and this type of ray was, this ray was used by the Thomson experiment. Okay. So, in Thomson experiment, so this ray was used and then apply the electric field and magnetic field, see the deviation of this ray, and it was measured, the deviation was measured. So, that I will discuss in next class. So, I will stop here. Thank you.